the pride of the American fleet. The most sophisticated warship ever built, equipped with devastating firepower. The USS Nimitz, the world's biggest aircraft carrier. She owes her success to a century of innovation in shipbuilding. There have been 7 key stages in the development of aircraft carrier design, and 7 key carriers. At the heart of each vessel lies a major technological advance that allowed them to increase in size. One by one, traveling up the scale, we'll reveal the thinking behind each breakthrough. 7 ingenious leaps from big to bigger into the world's biggest. The Nimitz can cruise at over 55 kilometers an hour, sail for over 20 years without refueling, and house 6,000 men and women. She can detect threats over 500 kilometers away and launch a supersonic fighter every 20 seconds to intercept them. She is a masterpiece of military engineering. To understand how the Nimitz became the most powerful warship ever built means traveling back to 1916. Almost as soon as people learned to fly, the US Navy saw the potential of launching warplanes from the deck of a ship. That ship was the USS North Carolina. Reaching takeoff speed requires a long runway. But the decks of warships were crammed with weapons and equipment. There was no room for a long takeoff strip. So engineers had to devise a way of getting an aircraft up to takeoff speed on a very short strip.
The fundamental problem is down to a basic law of physics. If you want to launch a large mass in a short space of time or distance, you've got to give it a lot of stored energy very rapidly. This is the basic kind of technology that's been known for thousands of years, the slingshot. I store the energy by stretching the elastic. I put my aircraft in it, store the energy, let go, and it flies wonderfully. But of course, this isn't a real aircraft with a real pilot. The challenges of making it work in the real world are much more significant.
The solution came from the fathers of aviation, Wilbur and Orville Wright. In 1903, they made the first powered flight and went on to develop their own launcher, a catapult. Their design consisted of a 6-meter-high wooden tower. This held a weight suspended from a rope. As the weight dropped, the rope pulled the plane along a rail until it reached takeoff speed. The Wrights offered their launching system to the US Navy. But dropping a heavy weight on the deck of a warship was not such a good idea. The Navy went back to the drawing board.
So they came up with a better idea. Another form of stored energy on board was compressed air, installed in warships for things like launching torpedoes and so on. Compressed air can be released and give thrust. So in a simple way, we can use compressed air to release an aircraft from a warship.
In 1916, the US military tried out the idea on the battle cruiser USS North Carolina. Engineers built a 30-meter steel track at the stern of the ship. They used compressed air to shoot a piston down a cylinder. The piston used a rope to pull the plane along the track. But compressed air alone was not powerful enough to launch an 800-kilogram plane. To speed it up, they fed the cable through a system of pulleys. These multiplied the force and increased the plane's speed sevenfold. The system took years of trial and error to perfect. Before this invention, the might of a naval power had been measured by the size of its battleships. But now, the flimsiest biplane launched from a carrier could sink the biggest warship. The aircraft carrier had come of age. Today, catapults are at the working heart of the USS Nimitz.
Without the catapults, we have no other means of getting the aircraft off to do their missions. It's basically just a giant slingshot.
It's the task of the shooter to tune the catapult to launch aircraft of different sizes.
As a shooter, my job is to take the weight of the aircraft and the wind that we actually have over the deck and use that to determine a setting that we put into our catapult system to shoot it off the front.
Lieutenant Kozlowski adjusts her catapult to launch a series of F-18 fighters. Each catapult has enough muscle to throw a Land Rover a kilometer. The secret of its power lies hidden beneath the deck. Instead of complicated pulleys and wires, the Nimitz has a pair of cylinders slung below its runway. Inside these cylinders are pistons. The pistons connect to the plane through slots at the top of each cylinder. They fill the cylinders with pressurized steam, which shoots the pistons and the plane forward. To prevent the steam escaping, they fit two strips of flexible metal that act like zippers and reseal the slots as the pistons pass through.
They'll salute us before we send them off the bow, telling us that they're ready to go. And then we'll hit the fire button.
On land, it takes over 1,500 meters to get an F-18 airborne. But the steam catapult does it in less than 100. But in 1916, the USS North Carolina had a huge drawback. No deck for her planes to land on. So they had to land on the sea and then be winched back on board again. Hardly practical for a ship at war. Solving the problem would require British ingenuity and a new kind of ship. In August 1917, Royal Navy pilot Edwin Dunning attempted the first landing on a moving ship. The obstacles he had to negotiate included the ship's central bridge and funnel, known as the superstructure. In a truly audacious move, Commander Dunning swooped sideways in front of them and landed on the front deck. 5 days later, he tried to repeat his trick, but as he touched down, the engine stalled and he lost control of the plane. The deck crew tried to grab the powerless aircraft, but strong winds blew it over the side. Dunning was knocked unconscious and drowned in his cockpit. Commander Edwin Dunning proved that a deck landing was possible, but it had cost him his life. Making the deck safe for landing would mean redesigning the ship's superstructure, the obstacle that had blighted Dunning's approach.
One proposed solution was to split the superstructure into two parts, moving them either side of the flight deck.
But the gap between the two blocks was hardly wide enough to allow a plane to land, and the designers feared this would unnerve their pilots. They considered removing one of the blocks. Not such a good idea. The Royal Navy searched for a way to offset the weight of the block they now called the island, to correct the ship's balance. They tried filling the port fuel tanks whilst leaving the starboard tanks half empty. But as she began to run out of fuel, the ship started to list again. Then they tried moving the entire hangar to port, leaving behind an empty space. But the crew soon filled the void with equipment, and the ship regained its starboard list. Finally, they decided to physically extend the hull outwards on the port side and shifted the heavy machinery to balance the boat. After 2 decades of trial and error, the Royal Navy now had a truly revolutionary design. HMS Ark Royal was launched in 1937. She was the mother of all modern carriers. Her island sat on her starboard side, making space for a long, clear flight deck. Her layout provided the template for every carrier to come, including today's Nimitz. The flight deck of the Nimitz has been called the most dangerous workplace on Earth. Here, the deck crew must dodge wings, blades, and jets as they fuel, arm, and park the multi-million-dollar warplanes.
Turning starboard, heel to port. Watch your moves, watch your step.
Engineers mirror the layout of the flight deck in miniature to keep track of the comings and goings of each aircraft.
On L1, 404. We'll take him back to L4 and we'll stuff the hole right there.
It's literally nuts and bolts technology.
This is the Ouija board. This is a miniature version of the flight deck, and these little plastic pieces that we have here keep track of aircraft that we actually have out on deck. Now these nuts and bolts, they represent different things. This means that it needs an aircraft that needs to be turned, its engine's turned, and then this one means it needs fuel. It helps us keep track of everything going out on the flight deck since it moves at such a fast pace out there. They're constantly updating this board.
Got to get him out. I got to clean up L4. I've got to drop this guy down off into the hangar. And if you want, you can put 203 on the elevator. It really doesn't matter to me.
This is always reliable. If we have a power outage, I could always rely on this being up and running.
Hey, before you put something in L1, make sure it's got missiles on it, right?
The Nimitz can operate more aircraft than any other carrier in the world. Up to 90 warplanes. In 1938, the biggest British carrier could only handle about 50 aircraft. American admirals wanted to double that number. But there wasn't enough room in their hangar to store the planes, even with their wings folded. So the deck had to take the overspill. This was potentially disastrous if an aircraft misjudged its landing. To solve the problem, the US Navy had to look to the past for inspiration. From the time of the earliest carriers, engineers had experimented with ways of slowing planes down by snaring them with so-called arrestor wires.
Well, the earliest systems consisted simply of ropes attached to pairs of sandbags. And the aircraft would come down and engage this rope, but of course one set of sandbags was not enough to stop a heavy aircraft. So as the aircraft proceeded down the flight deck, it had to engage successive pairs of sandbags until there was enough resistance to stop the airplane. This simple system, of course, was nowhere adequate for high-performance aircraft, so other more complex systems had to be developed.
On the USS Hornet, they had to stop a heavy warplane landing at over 135 kilometers an hour in just 45 meters. This is how they did it. As a plane lands, a hook on its tail snares a wire and pulls it forward. Beneath the deck, this action forces a ram into a cylinder filled with fluid. The plane's momentum is dampened as the fluid is squeezed up a tube and through an opening made ever smaller by a closing plunger. An elegant idea, but in practice, snagging a single wire proved difficult for pilots to do. So the engineers lined up several wires, one behind the other, to increase the chances of a successful grab. But even this didn't guarantee success.
During the Second World War, it was fair to characterize the landings as looking like a controlled crash. As the pilot approaches the back of the ship, he's going to fly his airplane into position just above the wires, and then he hopes that the airplane will drop right into the middle of those wires and pick up one of those 12 wires. If they didn't catch any of the wires, then they had 5 what they call Davis barriers that would engage the landing gear on the aircraft and stop it that way. Unfortunately, these Davis barriers normally would flip the airplane upside down, but it would definitely stop.
Today, on the Nimitz, they use a similar arrestor wire system. But trapping the wire has become even more difficult. Jets hit the deck so fast that the pilot has precious little time to guide his plane onto the wire. It's so hard that pilots have to practice over 100 simulated landings before they're allowed to try the real thing.
Now, landing on a carrier is a lot different than landing at a long airfield with 12,000 or even a 5,000 foot strip. This is what we call the dirty configuration. I've got my gear down, my flaps are full, my hook's down, ready to catch the wire. And there's no mistaking it. When you catch wire, it's a lot like a mild car crash. It throws you forward in the straps, and you definitely know that airplane's going to stop.
The jets landing on the Nimitz push its arrestor system's braking power to the limit. It has to bring an F-18 traveling at 225 kilometers an hour to a stop in just over 100 meters. About the length of a football pitch. The quality of each landing is assessed by senior pilots standing at the stern.
We will grade them on their start, the in-the-middle position, at the in-close position, and then again as they cross the ramp.
And then the grade goes into an overall grade point average for how everybody's doing.
Every pilot in every squadron thinks they're the best.
Definitely me.
Who's the worst pilot?
That guy.
The arrestor wire allowed planes to land safely on a crowded deck. But during World War II, the deck itself became a target for enemy bombers. Protecting the ship from bombs would demand a total rethink, and was to double the size of the aircraft carrier. June the 19th, 1945, a naval catastrophe. Japanese bombs penetrated the USS Franklin's wooden flight deck and exploded in the hangar below. 724 American sailors and airmen were killed. The US Navy resolved never to allow this to happen again. They decided to protect the crew by replacing the wooden flight deck with armored steel. But this caused huge problems for ship designers.
When you replace a deck made out of wood with one made out of armored steel, your real issue is to do with adding top weight and making the vessel top heavy. This causes the vessel to reduce its stability, which makes it vulnerable to capsize in waves.
To make the ship more stable, the hull has to be made wider. But a wider hull meets more resistance than a thinner one and impedes the ship's movement through the water. To restore speed, they had to make the hull more streamlined. This made the ship longer, but also heavier. The mighty USS Midway was the product of this thinking. She weighed almost twice as much as her predecessors, and for the 10 years after the Second World War, she was the largest ship in the world. Her deck was protected by 3 acres of armored steel, 9 centimeters thick. It shielded her so well that she served for 47 years. The deck of the Nimitz is also made of steel, but it isn't armor-plated. It doesn't need to be. No attacking aircraft should ever get close enough to drop a bomb on it. Layer upon layer of high-tech protection stands in the way. First, long-range radar scans the sky for intruders. Should there be any, she directs her fleet of F-18 fighters to intercept and destroy them. If an enemy missile does get through, it will meet her next line of defense. A ring of missile-armed warships. Finally, the Nimitz can unleash her own missiles, each capable of destroying anything that gets within 8 kilometers. These defense systems are operated by the tactical team from a bunker deep within the Nimitz. Back in 1945, the Midway's armored deck protected her well enough against enemy bombs. But her aircraft were outdated. In the 1950s, Navy commanders wanted jets on their carriers. But jets flew too fast to land safely. It would take 10 years and one inspired Royal Navy pilot before the next breakthrough could be made. In December 1945, a jet managed to land on a carrier for the first time. It was an extraordinary feat of flying by Eric Winkle Brown, the Royal Navy's top test pilot. But it was a one-off.
That aircraft there is the aircraft that Winkle Brown landed in December 1945 and made carrier aviation with jet power fundamental to any modern navy. It also identified that there were a batch of new problems to be resolved.
The main problem was that fast jets also had to land fast. This left their pilots less time to find the correct angle of approach. If they came in too steep, the aircraft would hit the deck too hard. But if their approach was too shallow, they risked clipping the stern of the ship. Engineers discovered the optimum angle of approach for a safe landing was 3 degrees. But it was almost impossible for a pilot to get this right every time. In slower propeller planes, pilots had time to respond to instructions from a man on the flight deck who used paddles to help guide them down. Former Royal Navy pilot Nick Goodhart explains how it was supposed to work.
So we're curving in, and he thinks I'm a little bit too high, so he makes a signal. And I say, ah, yes, a little too high, and I throttle back just a little bit and descend a bit, and then he said, no, too low. And I open the throttle a bit, and sure enough, we're on a reasonably good landing track, and I get near the round down, and just as I'm coming over the round down, he makes the signal cut, and I chop my throttle, and we descend gracefully onto the deck, and everybody's happy.
At least that was the principle. But Goodhart discovered it was a very dangerous procedure.
In fact, we lost so many pilots that way that it exceeded by far the number who were killed by the enemy in the war.
Appalled by such losses, Goodhart himself came up with a simple idea that enabled the pilot alone to find and follow the correct angle of descent.
We've got this rig set up here, which was the rig that I used originally in my boss's office. I set up a mirror, which I had borrowed from his secretary, on the carrier deck there, and that mirror has a line across it made out of lipstick to mark its middle. And I also had a torch, which we got here. So we set the torch up on the carrier as well. And then we invited his secretary to come in, and I said to her, look, now your job is, as a pilot, is to see the reflection of the torch in the mirror and walk very slowly towards it, keeping the reflection on the line.
By keeping the light level with the lipstick line, the secretary, like the pilot, would naturally follow the correct angle of descent. Translated onto a ship, this is what's happening. The torch is represented by 4 lights fixed to the deck. Beyond them is the mirror. A row of lamps represent the lipstick line. As the plane approaches, the beam from the deck lights reflects back to the pilot at an angle of 3 degrees. So if the pilot keeps this reflection in the center of the mirror, he will come down at the right angle. But it's not as simple as that. At sea, a ship pitching in the waves throws the beam about, sometimes with devastating results. To stabilize the beam, engineers fixed the mirror on a gyroscopic mount. Now a plane could safely follow the right line of descent, however rough the sea. This British invention was so good that the American Navy immediately appropriated it. And in 1955, their brand new supercarrier, USS Forrestal, put the ingenious device into practice. It allowed a whole new generation of supersonic fighters and nuclear-armed bombers to land on her decks safely. Today on the Nimitz, they use an improved version of Admiral Goodhart's landing aid. Pilots call the central lamp in this row of lights the meatball. It is fitted with a special lens so that the approaching pilot can only see its light when he lines up his aircraft to come in at the correct angle. The system stands up well to the demands of modern warfare and its frequent night operations. On a clear night, pilots can see the meatball as far as 6 kilometers out. Even so, trainees are not allowed near a real plane without conducting 10 hours of simulator rides first.
Now at night, or in bad weather behind the ship, the instrumentation is critical. Right now I'm at 1.9 nautical miles. At this point, I can't see the meatball at all. I'm relying solely on my instruments. Again, on dark nights like this, where it's really rough, a lot of illusions out there, hardly any depth perceptions. First step is to get in this aircraft below 250 knots. And then nights like tonight, it can be a real heavy workload. The pace quickens, you're getting a lot of wind gusts. So the whole way down, I'm making small trim adjustments until I get it stabilized. About 1.5 miles, I can start picking up the lights of the carrier box, which is the landing area. It's a great feeling when you pick up the meatball because now you know you have a good visual indication to the proper landing point. Right now, show me a little high. It's coming down into burner. There's a good trap.
The mirror landing aid allowed the Forrestal to carry the world's fastest Navy bombers. But as a fighting ship, she had a severe limitation. She would run out of fuel after only 3 days of action. A new propulsion system was needed, but it would weigh so much that a much larger ship would have to be built to house it. This is the start of a dangerous operation for any carrier, refueling at sea. A conventional fossil-fueled carrier drains her tanks in about 3 days, and then needs a pit stop. But it's not just a matter of a quick top-up. First, the crew has to use a pilot rope to pull across the fuel line. Then, once the line is connected, they transfer more than 2 million liters of fuel. The process ties the carrier to a slow tanker and leaves both vulnerable to attack by enemy aircraft and submarines for several dangerous hours. There had to be a better way. One solution: harness the colossal energy released by the splitting of an atom to produce nuclear power. Scientists discovered that firing particles at atoms of uranium loosens the bonds that hold their tiny components together. A chain reaction in a nuclear power plant in the bowels of the ship triggers a massive release of energy in the form of heat. This heat can then be used to generate steam. Shooting the steam through a turbine forces its blades to rotate at high speed. And transmitting this movement through a set of gears generates enough turning power to spin an enormous shaft attached to a propeller. 4 of these propellers together have the power to push 91,000 tons of metal through the water at 55 kilometers an hour. But nuclear power came at a price. To protect the ship's crew from deadly radiation, the engineers had to shield the reactor with hundreds of tons of lead. But a supercarrier needed 8 reactors. And in heavy seas, the extra weight in the middle of the hull could have caused the keel to buckle. So they strengthened the keel with a honeycomb structure of steel cells. These took the weight of the reactors and led to the birth of the largest carrier the world had ever seen. The USS Enterprise took to the sea in 1961. Her 8 reactors made her the largest nuclear power facility in the world, able to generate enough electricity to supply a city the size of Leeds. And she had one colossal advantage over conventionally powered carriers of the day. She could sail for 3 years without having to be refueled. Today, a Nimitz-class supercarrier only needs to be refueled once every 20 years. And just 2 modern reactors supply her with all the power she needs. The space that once might have been used to store fuel for her engines is now used to store fuel and ammunition for her jets. Her reactors send electricity down 1,500 miles of cables to support this city in the sea. 6,000 heads lie on 14,000 pillowcases between 28,000 sheets. Each day, cooks prepare 18,000 meals from their supply of 120,000 eggs, 15,000 kilos of potatoes, and 11,000 kilos of meat. But it can be a lonely place.
The The worst thing about it, being on the Nimitz, would probably be being away from family.
Being away from home.
It's the same day over Groundhog Day.
Every day is Groundhog Day. We always joke about it. Every day's Monday.
The camaraderie of the pilots out here is probably the only thing that makes it so you can survive with your sense of humor and with your sanity.
Over the past 30 years, this floating community has demonstrated its prowess by delivering air power straight to the heart of the enemy. The Nimitz was commissioned in 1975. She proved so successful that the US Navy would want 9 more like her. But it took a long 7 years before the first one was built and ready for service. And there was only one dry dock in the whole of America big enough to handle a Nimitz carrier. There had to be a quicker way of building the carriers of the future. Until 1981, the US Navy constructed their carriers like office blocks, building from the bottom up. Each one contained enough cable to stretch from London to Moscow, used 45,000 tons of steel, and needed an army of workers.
A huge range of craftsmen were involved. Boilermakers, shipwrights, carpenters, electricians, and so on. And that meant that the ship grew very slowly. It tied up a dry dock for a long time.
In the congested compartments, the electricians got in the way of the plumbers, who got in the way of the welders. That's why it used to take 33 million man-hours to construct a carrier. Today, they build Nimitz carriers on the dockside, section by section, and then weld the pieces together afterwards. The specialist trades take turns fitting out each module with its cables and electronic systems, its bulkheads and passageways. And as they are no longer in each other's way, they build the ship much faster. A job that once took 3 hours to do in a traditional yard now takes just 1 using the new modular method.
They're very, very large pieces that go together. The improvements in computer design, the ability to reduce the number of pieces that go together, it is going to be a heck of a lot more efficient.
They use the biggest crane in the Western Hemisphere to move the modules into position. 161 modules come together to make a carrier. Each can weigh up to 850 tons. Moving the modules pushes the gantry crane close to its lifting capacity. On July the 8th, 2006, workers craned the final piece of the jigsaw into place. It is the carrier's mighty 700-ton nerve center. Finally, after 3 years of construction, the shipbuilders flood the huge dry dock. Mission accomplished. The latest and last of the Nimitz class of carriers takes to the water. So far, the Nimitz carriers have given over 30 years of service. They remain unchallenged as the biggest and most advanced warships in the world. That is, until someone builds a bigger one.